So the three of us leading the spectral theory group, me, Matt Faust, and Stephen Shipman, we're each going to present something now. And the reason there's three of us is I got to leave because my daughter's getting married this weekend. She was born here in Toronto 27 years and 2 days ago, just down the road at a hospital down there. So it's cute. Yeah, but I'm sorry. In general, I don't like leaving conferences early. I think it's sort of general bad manners, but I got to do it. I'm sorry. So a couple of rounds. So briefly, those of you who are interested in spectral theory or are assigned to our group, that may not be the same. We're going to go to lunch together, okay, and talk about things. And also, and like I said, we're going to talk about, each of us are going to talk about a different aspect of some problems people might want to consider. They're not necessarily direct follow-ons from work that's been done recently, but there are projects we think are appropriate for exploration with people with a commutative algebra, algebraic geometry background. So I'm going to talk about homological algebra and periodic operators. Now, homological algebra, free resolutions, Betty numbers, cohomology, etc. They're an important theme in commutative algebra. And I know this because we teach a course on commutative algebra and homological algebra at Texas A&M. Well, not we, the other people do. Like my wife. Anyways, so last time I showed how a periodic operator, so I have a periodic, this is a periodic graph. My handwriting is really bad. You can see why I'm going to try to write little. This leads to a matrix, which I wrote as h of z of Laurent polynomials. And now, given this, its characteristic matrix, this is the identity matrix. It's a map on, well, it's a map of free modules. Like, okay, it's actually an endomorphism of this free module, and the kernel sheaf of this map is, well, these are functions where hz of the function is lambda times that function. They satisfy an eigenvalue problem. Okay, so there's that we call that they solve a spectral problem. So this has a kernel sheaf. So the which I called the block sheaf because I'm channeling Peter Cushman, who's someone in my block sheaf. Chalk day. And this is supported on this algebraic object, this geometric object called a block variety, which I was talking about, and particularly some geometric aspects of it. Sorry. Okay, so that's the input from last time. Now, and the block variety is the variety of, the determinant of this characteristic matrix. So it's a hypersurface, and there are various features of it I talked about a little bit, and people write papers about that. Now, I want to point out that this setup of having a matrix of Laurent polynomials, okay, this is a special matrix of Laurent polynomials that you get from an operator in a periodic graph. But I want to say that there's actually nothing very special about this. Any matrix, so I'm going to n by n matrix of Laurent polynomials. Any such matrix gives it's the same thing as an operator. I mean, they're just reformulations on a directed periodic graph. And this is almost a tautology if you think about it. And what's the graph? So the vertices of the graph are simply, so this is n by n, so they're the column or row indices times your, I'm going to assume z to the z, d is my, okay, these are d variables. So these are the vertices, and then you have an edge between some, u plus alpha. So u is a number from 1 to n, alpha is an element of z to d. There's an edge, there's a directed edge. So maybe I'll do it this way, and v plus beta. okay, so my edges, you have an edge here, if and only if z to, and this is a choice, I'll just say alpha minus beta, probably it's beta minus alpha, appears. So this monomial appears in position, well, so my matrix 8 in H sub u comma v. So if you look in this slot of the matrix, there's a Laurent polynomial, and if there's a monomial z to the alpha minus beta, then you have an edge in your periodic graph, right? Or you have a directed edge. And lastly, the constants. Oh, right. Okay, so that's the graph, and then but there's also, it's a weighted graph, and the coefficient of this monomial is the label. And the last part, so I'll slide this up. The last part is that the constant term in position, it was m u u, is the potential at u. So just for the matrix, you write down, you get a graph, periodic graph that's labeled, and it has an operator the same way I talked about, except for some of the directed edges that have undirected edges. So there's really nothing too special. I mean, if you have, yeah. So when the matrix has this property that its transpose is Z inverse, then it will be, yes.
You said that the coefficient is the label. Do you mean that's like the weight of the edge?
Every directed edge has a label, which I'll call a weight.
Okay.
Yeah, I called it a weight.
Okay.
Yeah, I mean, the problem is, you can call it, the problem is, as I said, when you work in different fields or maybe different human beings, they give different names of the same thing. And if you're me, you give different names of the same thing in the same talk, and you get a yellow card. Okay, so now the point, what I want to say is I think it's an interesting problem that's begged for in this topic, is use anything about homological algebra to study block sheaves and block varieties. You can also, if you fix lambda, then you're going to look at a level set of this, and you're going to look at the solutions that have the eigenvalue lambda, and those are called Fermi varieties, and you can restrict the block sheaf to the Fermi variety. So say anything about any of that. Yes. Polynomials. Polynomials. Yeah, I mean, yeah. So it's yeah. The number of edges emanating from a vertex could be bigger than one. A number of edges, from one vertex to a translation of another. There's one edge from one vertex to a translation of another vertex, but there could be several such edges to different translates given by the different monomials you find in that entry. Is that okay? Yeah. I mean, it's almost a tautology. So now an example of this is, so in our reading, which everybody in our group read, there's a paper by Kravaris, and what he did is he studied compactly supported eigenfunctions for H at a given energy lambda, and these are special. These are ones where the whole determinant. So you can have such a compactly supported eigenfunction when this determinant is identically zero, so it vanishes. In general, you have this determinant, it's a polynomial, and where it vanishes, you have something. But this is the case where it's called a flat band. I showed a picture of that. So he studied this using homological algebra. He showed that there's a module of such these, and he computed its Hilbert series. Now, the one thing that I want to add to this before I quit is all of this is happening geometrically over C star to the D, maybe cross a copy of C for lambda. That's the underlying geometry behind this, under this ring here. That's the spec of that ring. But in this field, people have studied, inside here you have the block variety. You have this, you have the kernel sheaf is supported on the block variety. People have studied compactifications of this, and also compactifying the block variety. And so I'll say that in some cases, because we don't really know all that you can do or how to set it up properly, because there's actually some really bogus stuff in the literature. where they're taking like square, like nth roots of variables and trying to say that gives us a toric variety. I don't understand what that means. In some cases, all of these guys, h of z minus lambda identity, and the operator. So there was originally a linear operator. These can be extended to a toric variety X, which contains, sorry to write in small font, this no one can see that. So it extends to some toric variety which contains this either this or maybe it's or maybe I'll also C lambda, and this is work. So some aspects of this is some we've done recently with Jordy, Matt, and Stephen, and so some of this can be understood as a map of toric vector bundles or projective toric vector bundles, and I think it's a fairly fertile area to apply ideas from algebraic geometry or homological algebra to. And that's all I have to say, and I'm done. And it took me 12 minutes. Sorry. I'll raise the board for you. Okay. Yeah.
So is the choice of vector factorization?
Well, it's a problem that kind of came up as sort of a miracle in a paper that I did with some physicists recently. So I started working with physicists to try to figure out if the stuff I've been doing on periodic operators and reducible with the Fermi surface and so on was just, you know, if I was really doing anything useful with my life. It turns out that there's a particular reason that we're able to publish this paper, and it has to do with a certain matrix factorization regarding the matrix that Frank was just talking about. And so that's the question that I want to get to and pose, that it's an interesting problem in matrix factorization that turns out to be kind of, it just pops out kind of like a miracle in what we call AB stack graphing.
I explain matrix factorization doesn't mean matrix factorization as commutative algebras think of it.
Oh, really?
Yeah, just keep going.
Okay, so now you know I'm not a commutative algebraist. Yes. So I want to talk. So I'm going to start with a certain eigenvalue problem. Let's go back to the periodic operator H. Now H of Z turns out to be this the version of it that Frank just talked about. Let's think of H as the operator acting on a periodic L2 of a periodic graph. Okay, so this is going from L2 of some vertex set to L2 of the vertex set. And so this is what we call the Hamiltonian. And so this vertex set is periodic and it has these edges, right? And then you can write this using the Fourier transform as this H of Z that we've been talking about, okay, as a modular homomorphism. One of the interesting problems in physics has to do with defect states. So if I put a local defect on H, so I add some potential V, where this V in the whole periodic graph, it vanishes everywhere except at a finite number of vertices. So that's called a local defect. And you want to know if a local defect can produce eigenvalues. So we're looking for solutions to this problem where U is actually an L2 function. Why L2? It's not just because we only care about L2, it's because that's where the H is self-adjoint, and that is also, you know, this is where the states, the quantum states actually exist. So we're looking for solutions of this, where this is a local defect. Now, H has certain bands of spectrum. I'll review this in just a second. And typically what happens is if this lambda is an energy that's not in one of the bands, then it's quite easy to produce to find a relation between the V and the lambda such that you have a solution to this. And so since the U is an L2, what it really essentially means is that you have this periodic graph, it might be graphene, you have a local defect, and then there's some state that's bound to that defect and it decays exponentially. And these things are bound states. produced by local defects. What's the interesting problem now is whether you can produce bound states when lambda is actually in the spectrum of the operator. And so this is something that is supposed to be physically not common. And the reason is that the spectrum of H, you can think of it in kind of loose terms as being sometimes people call it the radiation spectrum, because it's where you have states that we have block states. And the block states are thought of as being radiation. And like the physicists might say, well, how can you have a bound state when you also have radiation? Because the bound state is going to couple to the radiation, is going to leak, so it can't be there. But if you're in a gap of the spectrum, then it does make sense to have a bound state, because there are no, what they call, there are no radiation channels that can take away the energy. Okay, so that's kind of the vague physicsy way of describing it. All right, so let's take a look at this problem, and I want to parse it in a slightly different way. Suppose I now take the v times the u and I put it on the other side, and I just call this f. So this is now I can this is a u, that's the state multiplied by a compactly supported potential, then this now becomes a compactly supported what we call a source or a forcing function. I'm sorry? I do. Thank you. Now if I just look at this problem here, we think of this as being a source function, and we think of the u as being the response. And so the question is it possible to have a localized forcing function at a frequency in the continuum so that the response is an L2 and it's not radiating? See? So that's another way to think of the physical problem. Okay, so let's now write this down in terms of the algebra. So we now will represent this Hamiltonian as H of Z. So this is now our the same matrix that Frank was just describing, but is indexed by a fundamental domain. We often call it H hat because we think of it as being the formal Fourier transform, but we can just take the hat off. So this becomes our module homomorphism. And so we're looking at H of Z minus lambda applied to, now we're going to think of this as U of Z equals F of Z. So I'm being sloppy and not putting hats on everything, if that's all right. So this problem here becomes this problem of algebra. So this here now is a vector of Laurent polynomials. It's this is this u and the f and all these vectors of z. They live inside R to the. So this w from Frank's talk yesterday was a set a finite set that's the fundamental domain of the graph. Okay, which Frank just called N. And this R here is just C, Z, the inverse, where Z is in C star to the D. Okay, so you have these D different variables. Okay, so let's take a look at this problem here, and let's write it as, let's write the solution, the response. This is now a vector of Laurent polynomials. Let's write this as, let me take the inverse of this object here. Let's write it as R of Z lambda divided by the determinant. So this is F of Z. This is just the adjugate matrix of H of Z minus lambda. And then this is the determinant, which we call the dispersion function. This is the object whose zero set is called the Bloch variety. And if you fix a particular lambda, then that's called the Fermi variety. Okay, that's what the D was. And so here's the forcing, and here's the response. Now, recall that lambda is in the spectrum means what? Lambda being in the spectrum of the operator is the same thing as saying that the intersection between the compact torus inside of Z space with the zero set of D for a fixed lambda, right, inside of C star to the D, that this intersection is not empty. So it just means that there are some Z's on the torus for which the D vanishes, which means that this, the inverse of this operator actually is singular on the torus. And why that's important is because when you go back to spatial space, when you go back to the graph, you have to do the inverse Fourier transform. And you try and do the inverse Fourier transform with something that has singularities on the torus, you get something that's not in L2. If you want to get a response that's in L2, then you have to make sure that this denominator, or this whole thing here, does not vanish anywhere on the torus. Okay, so now, here's the thing. Suppose that this D here is actually reducible. Then that means that the response is equal to R of Z lambda times F of Z divided by D1 of Z lambda, D2 of Z lambda. Now the D1 and the D2 are the irreducible components of the Fermi surface for a fixed lambda. So fix the energy, and I don't care, so what I do care about is that these two are Laurent polynomials in Z, and not monomials, so this is genuinely reducible. And we don't care about how it depends on lambda right now. It does not have to be polynomial in lambda. So we're not talking about reducibility of the Bloch variety in Z and lambda, but just reducibility of the Fermi variety for a fixed lambda. Okay, suppose that these are, just for the sake of the argument, suppose that these are irreducible, and this just has two irreducible factors. Well, in order for the lambda to be in the spectrum, all that you need is that one of these two is vanishing on the torus somewhere. Suppose that the D2 vanishes somewhere on the torus, on the compact torus, and that the D1 does not. All right, so let's say that this is not equal to 0 on the torus. So here's what we would like. We would like to choose F's that cancel all of the singularities on the torus. And there's a basic theorem of Kuchman and Weinberg. And the paper where this was really this idea was first put forth, and the idea is that if you want the output to be an L2, then you have, in order to cancel all of the singularities on the torus, you have to identically cancel the irreducible component as a polynomial, or as a Laurent polynomial. And so this numerator has to cancel the D2. So we want this to look something like a vector divided by D1 of Z lambda. And so what we're looking for is the following. We're looking for, see, so this here is some interesting Laurent polynomial matrix. That's the adjugate, right? And then we're looking for vectors F of Z such that this is in the ideal generated by D1, all of the components, or D2, but not D1. So we want this to be.
What's the R you said together now? What's the R called?
The R is the adjugate.
I understand,
Yeah.
but in this context,
We just call it. I just call it the adjugate. Yeah, yeah. So 0 modulo D2 and not identically 0. What did I say?
Yeah.
Yeah.
You
My D2, D1. So I want some singularities here in D1, and the reason is that it would be nice. We don't need to worry about the reason too much, but I want this not to be a polynomial. If we factor everything in the denominator, I mean, if we cancel everything, then we actually get a polynomial as the output, and therefore that means that the state itself U has compact support, has finite support. All right, and so we're looking for this. So this is really about matrices, Laurent polynomial matrices, and trying to understand when you I mean, look, you can think about the singular set of matrices or the zero set, but here what we care about is when you apply it to different vectors, right? Laurent polynomial vectors, what ideals do these things live in? Now, there's of course an obvious answer that you can always take this f of z to be d2 times some vector. Okay, obviously. But what we really care about, and this is what actually allowed us to publish this one paper in physics, was that you are looking for the minimal f, sorry, the minimal, yeah, f, for which this happens. So what do I mean by minimal f? What I mean is minimal number of monomials. Ideally, what we would like is for this f to be a constant. That would be very nice and have a lot of zeros in it. Okay, so I'm going to show you a situation in which this happens very easily.
It's like you have a set of syzygies.
Yeah,
R gives you syzygy,
that is
you
right.
give somebody that's solved.
That is right. So somehow you're trying to get this.
Where's the syzygy of the column?
So you see, yeah, that's right. So if this were a constant vector, you somehow the entries of R are conspiring to bring out a D everywhere in every single component. And you don't expect that to just arbitrarily happen for if you just write down some matrix R of Z. But what happens, how much time do I have? Can I take 5 minutes? What? Okay. Okay, good. So here we go. So I want to show you a situation in which this happens automatically. And this, if you have a graph, a periodic graph, starting at the beginning up here, that has certain symmetries, then you can get this H to block diagonalize. And so the typical example is the silly example is if I have 2 copies uncoupled, then I just have 2 copies of the same thing. But you can have 2 copies of, let's say graphene, hexagonal lattice. And you just, so let's say one of them is here, hexagonal lattice, and another one is aligned directly below it. And then you connect them with edges, just each vertex to the one below it. And so you have this symmetry about the middle. Then what you can do is you can decompose the operator into the even, its action on the even and the odd states. And when you do that, you're just block diagonalizing the H of Z. So let's say the H of Z is now block diagonalized to H1 of Z and H2 of Z. Okay. And I'm saying under the appropriate basis, let's say it becomes this under the appropriate change of basis. Then this R of Z lambda just turns out to be, okay, let's say that the adjugate of H1 minus lambda, I'm going to call it R1. The adjugate of H2 minus lambda, I'll call R2. And so that means the adjugate R of this H is now, I don't know what this thing is. D2 of Z lambda, R1, 0, 0, D1 of Z lambda, R2. And the reason, of course, is that if I divide this by D1, D2, then this goes away and I have the R1, R2. All right, so now you just take a look at this. If I multiply this thing here by anything that looks like a vector in the first component and a 0 in the second component, I automatically get a D2. Okay, that's just because it was block diagonal. And this is coming from symmetries. So the title of this paper with the physicists is called something like Bound States in the Continuum for AB stacked graphene without symmetries. So how can you achieve this kind of a thing if you do not have symmetries? So it's kind of understood in physics in not just for periodic media, in optics and different things, that if you have symmetries, then you can try to use those symmetries to get embedded eigenvalues. But if you don't have symmetries, it seems to be a really difficult thing to do because they have to just somehow appear. What we show in that paper is that we use the algebraic structure of this reducibility to get these embedded eigenvalues. And not only that, but also that we can put the defect V, which has to do with the support of the F on a very, very minimal set. Okay, and so this has to do with the matrix factorization. So I want to show you what happens in the case of what we call AB stack graphing. I'm going to write down the H of Z for AB stack graphing. So it looks like this. So graphene has a single layer, has two vertices, and they repeat kind of like chicken wire. So you take this, repeat it periodically, forever, and then you take two stacks, or two copies of it, and you shift one relative to the other. So one vertex of the upper one lies over the hexagon of the lower one. Now just write down what the Hamiltonian looks like. It looks like this. So we get 1 plus Z1 inverse plus Z2 inverse, 1 plus Z1 plus Z2, and then you have another copy of the same thing, 1 plus that, plus that. And this will be just two copies, but then what you do is you can put some, what they call a gating. You put some number here. This is if you put an electric field across the bilayer graphene, and then you couple them like this with the gamma right there, rather than on the diagonal. This is called AB stack graphene. There is no way that you can block diagonalize this in a way that is polynomial in Z. Okay, but it turns out that the dispersion polynomial actually is reducible for certain reasons. And I'm going to show you how this matrix factorization works. So this is kind of the, let's see, where should I write? Okay, that'll do. That'll do. So the matrix factorization goes like this. If I do H of Z minus lambda, there's an upper block. If you use the right basis, there's an upper block diagonal and a lower block diagonal matrix that converts this into something that looks like a 2 by 2 matrix and an identity with some special properties. Now I'm going to take the inverse, H of Z minus lambda. Inverse now is equal to L, and then the inverse of this thing, S inverse I and U. And now this is a factorization that has some really nice properties. And it has the following property, that the first of all, S, so there's an identity matrix here. This S here, everything depends on Z and lambda. And it turns out that the S has eigenvectors. It's a 2 by 2. And I could write it down if I needed to, but it's kind of long. So it's a 2 by 2. And its eigenvectors are independent of Z. That's kind of a miracle. Its eigenvalues are exactly the factors D1 and D2. This is also not necessarily expected, right? So the D is the determinant, but it doesn't mean that the two factors are necessarily the two eigenvalues. But it turns out to be that in this case. Those two things are important. And the other thing is that this U is invariant on the eigenspace of the S. And so what happens is you can take the eigenvectors of S, you apply them to U, they don't change. Then you do the S inverse, and if you take the right eigenvector, you're going to get the D1 inverse out and not the D2, and you get exactly what you want. And what's really important is that these eigenvectors do not depend on Z. What that means is that we're talking about a forcing function, F, that doesn't really depend on Z. It's actually a constant. That means that this F in space actually is localized just to one fundamental domain.
Like a quantum dot.
Yeah, it's just plus there are a lot of zeros in it too. It's like it was. So it turns out that instead of having to put the D2 in the actual F, that would require putting a potential on 28 different sites that you would have to somehow in the lab manufacture. But it turns out you can just put it on 2 sites. And that's a kind of miracle. It just happened because we were messing around with some kind of intuitive, just some fake intuition right, about the physics and came up with this factorization. But the question is, why is it really happening? And what kind of graphs allow this kind of factorization to happen so that you can localize the defect and get it in these embedded eigenvalues? I yield my time.
Matt has his own.
Okay. Can you hear me? Or no?
Yes, they can.
Yeah.
Okay.
Here, let me put this board for you.
No, I can't. I thought for some reason. Maybe the speakers are located. Oh, appreciate it. Luckily, this is a very easy problem to state, and there's not a whole lot that's been done in general, so I don't have to say very much to get it to pass. Yeah, so what I'm going to talk about is isospectrality for these operators, well, specific types of spectrality. I feel like every time someone brings up isospectrality, you have to mention the following question that I guess inspires it. The spectrality is often posed through the question, can one hear the shape of the drum? I'm not going to write it because I don't have time actually. This was popularized by a monthly article by Mark Kac in 1966. Although I'm sure this phrase came well before that. But anyway, isospectrality, as one could guess, typically refers to we want to study when two operators have the same spectrum. In our case, we're interested in a specific type of isospectrality. State, I guess, Fermion, Bokeh isospectrality. So rather than just requiring the spectrum to be the same, we want to know when do two operators produce the same block variety in our context. So our block varieties are, of course, hypersurfaces. This is the same as just asking when do, if I have two matrices that correspond to two different operators, when is the characteristic polynomial the same for varying parameters? So varying, in our case, either the potential or the edge weights for some fixed graph. I guess we introduced this kind of, okay, let me just.
Oh, right there too much, sorry.
Oh, good point. Okay, I can give an example if time goes, but I guess more familiar term that you all have encountered would either be inverse problems or identifiability. Problems, oh geez, let's see here, time. But in general for block varieties, most of the previous work done on isospectrality has been restricted to the square lattice. All right. So square lattice, Frank may or may not have introduced this, but this one, oh, fantastic, you did. We're just looking at operators on the phone graph. So this is the 2D variant, but just take z to the d and that allow for edges between nearest neighbors. This is referred to, of course, in 2D variant square lattice, but they'll just still say square lattice even for higher dimensions. The more foundational work on this was too much. There's a series of papers by Kaplan that first look into this. These are isospectral potentials on the discrete lattice. This is broken up into a series of 3 papers. And so you all can find them if you want to. The first one was 1988. The second one was also 1988. Advances for applied math. And the third one was in transactions in 1989. Okay. In these papers, he studied, in the first 2, it was mainly studying what happens at a generic potential. And it turns out, so mathematical physicists are typically interested in real isospectral potentials. And in our case, we had some edge operator, but they were always fixed that to be 1, so just take the standard Laplacian. And in this paper, he studied what happens at a generic real potential, and it turns out the only real potentials that are isospectral to your original potential, so like yield the same block variety, or okay, so spectral, and I actually wrote it. Real potentials that are isospectral to a generic real potential, so just randomly chosen real potential, are given by the symmetries in the graph. So what I mean by that, well, if I have, let's say, a 2z by 2z periodic potential, means I only can possibly have 4 potential values, since after I fix the values of my potential on these 4 vertices, the rest of the graph, values my potential can take are determined by these 4. Well, my choice by, I guess, drawing this square, I'm more or less choosing the fundamental domain, and in terms of our actual operators, my choice fundamental domain is arbitrary, so no matter what domain I choose, I'll get the same thing. So there's no reason I shouldn't have just chosen this instead. So of course, if I do one here, here. So if I swapped V1 and V2 and V3 and V4 simultaneously, I would get the same block variety. If I swap this row and this row simultaneously, I get the same block variety. So these are naturally induced symmetries that our graph has, and these are enforced on the space of focus special potentials. You necessarily have to have these. So I guess these are 1, 2, 3, 4. Then I would have 1, 2, 3, 4. Showing as a vector right now. And it's going to be isospectral to
Your P4 activity nodes.
P4. Yeah, exactly. Yeah, I should have said that. Yeah.
Parameter swapping.
Yeah, exactly. The third ladder work 3 kept it focused on special potentials. So when our space is not, when we don't have a generically chosen potential, what happens? There's particular interest in the 0 potential. So when we fix the potential to be 0, these are referred to as Unbar-Zoomian type problems. And in particular, you showed that you cannot have a non-zero real potential that's isospectral to 0. And this shouldn't be surprising, given that in 1 and 2, they showed that the only real potentials that are isospectral to a generic potential are those induced by these symmetries, and 0 is only symmetric to itself with respect to these graph symmetries. Okay, got a moment. Let's see what else we'll say. There's been, I guess, several. So this happened all in 1988, and then at least for discrete periodic operators, it's kind of like dormant until it's in the 2020s, where you wrote several papers, which I have 30 seconds around all time to list this, but he has wrote several papers, mostly focused on generalizing some of the open questions, or trying to solve some of the questions that were left open in this 1989 paper. Again, most of these are on the square lattice, mainly involved on separable potentials. So we would say a potential separable. So really, in this case, right, we can do our potential as some function in 2 variables, given space here, and a potential separable, if we can write it as just some function on x, or take higher dimensional analogs of this property. That's, I think, the main focus of all these recent works. So the question would be for you all, or whoever's in our group, is to study Fourier spectrality, but for more general models. There's also another concept called finite spectrality, but we definitely don't have time to get into that. But I guess to give one concrete question, one of the things I think would be interesting to classify is for what graphs does this property hold? By this property, I mean for what graphs are the only isospectral solutions, or the isospectral potentials for a generic potential that's real, just those given by the symmetries of the graph. And that would be one concrete problem to look at. But other than that, I'm already over time, so thanks, I guess.